All right, u of x, we're going to put it into standard transformation form. The parent function, of course, is x squared? I don't know. Help me out. What do we call that? Lean, mean graphing machine? The natural log of x. Yeah, very good. The natural log of x. All right, so the pi in the front and the e in the back both make up the what letter in the standard transformation form? The D, right. And those are both constants, but they're unlike terms, so we're just going to leave them as pi plus e. Pi is about 3, e is about 3, so pi plus e is about 6, right? Good enough. It's about 6. The 5 minus 5x over 6, we're going to first write that as negative 5, 6 times x in the front. So you want to kick the x out of the numerator so you can have the negative 5, 6 as the coefficient, but it is negative, and then we got the plus 5. And now, step 2, on the inside of the function, which is in the natural log, we have to factor out the coefficient of x. So we're factoring out a negative 5, 6. And we're going to be left with 2 terms, and therefore 2 sets of parentheses. Now, if you want to put the pi plus e in parentheses to group it together as your d value, that's fine. Now, the first term is going to be the less fun of the two. When you factor a negative 5, 6 out of itself, you're left with a 1x. So there it is. What do you get when you factor a negative 5, 6 out of a 5? Well, do that off to the side. It's the number on the right divided by the number on the left, or what you started with divided by what you factored out. So 5 divided by negative 5, 6, you could do your state change flip, and that would be negative 6 over 5. Of course, that's now 5 over 1. Your 5's divide out, and you're left with negative 6. Yeah. Now, you quickly check by redistributing. Negative 5 over 6 times negative 6, your negative 6 and your negative 6 divide out, leaving you a plus 5, and you know that you're correct. Very good. All right, so going through and listing what we're doing. What's the a value? It's just 1. So we're not doing anything with it vertically in terms of dilations or reflections. The negative 5, 6, though, is going to be an x-axis reflection. X-axis reflect. Xion, I guess we'll put that on the end there. And then the 5, 6 is your b value. It's less than 1, isn't it? 5, 6 is less than 1. So that is going to be a horizontal stretch or compression if it's less than 1 on the inside. No, you would think compression because it's less than 1, it's making it smaller, but on the inside it actually would make it bigger. So it's a horizontal stretch, and then by a factor of. Do we say by a factor of 5, 6? No. So because that number is less than 1, if you are doing the stretch and compression, you're saying which way it's going, you put the reciprocal of that number. So the reciprocal of 5, 6 is 6/5, which is also 1.2. Okay? So you're making it 1.2 times wider, or 6/5 times wider. You could just leave it as 6/5. Yeah? Oh, yeah, it is a y-axis reflection. I put x-axis reflection. Thank you. Yeah. I know better than that. I was focusing on the 5, 6 in my mind, and I think I even said x-axis reflection. So good catch there, Mr. Wench. Everyone's cognitive dissonance is now resolved? Right? Okay, good, good. Yeah, very good. That is a y-axis reflection. I would have caught that when we were graphing it, but better to catch it now so y'all can focus on this. Now it's a horizontal stretch by a factor of 6/5. Now y'all can absorb that. All right, I'm going to let y'all tell me what to do because I keep messing up on this Monday morning. The x minus 6, that moves the graph right 6? I'll take your word for it. And then the pi plus e moves the graph up 6-ish? Up 6-ish? Yeah. We'll just say up pi plus e. Sound good? Up pi plus e. All right, so the parent function, of course, is y equals the natural log of x. And this is an interesting function because it does have a restricted domain. It has the vertical asymptote on the y-axis, and it lives to the right. Now, because we have a y-axis reflection, that's going to take this graph and reflect it across what is essentially the vertical asymptote. So now the graph is going to live to the left of the vertical asymptote. And that affects the domain, doesn't it? So instead of everything to the right of the vertical asymptote, now everything to the left. Had it been an x-axis reflection, first of all, the negative would have been in the front of the natural log, but that wouldn't have messed up the domain. That would just make it open downward to the right. This one now opens to the left. All right, the horizontal stretch, 1.2 times wider. If you want to actually grab that and move it, it's going to be like that. But again, that just affects the steepness of the graph. So we're not going to have to show that. Right 3, is that or right 6? I'll get it right, hopefully by Wednesday. Right 6, is that an important one for this graph? It is, because what's the only transformation that'll relocate a vertical asymptote? The horizontal shift. So the vertical asymptote, which was at x equals 0, is now at x equals 6. Now the up pi plus e, if you want to grab either one of these final graphs, move them up and down, that doesn't really matter, okay? That's not a critical one. So we're ready for the final graph, I believe. Y-axis, x-axis. The first thing we want to put down is the vertical asymptote. In any case, when you have a horizontal or a vertical asymptote, you put it down first. And now the graph lives to the left. All right, so here we have some choices. It's either going to look like this, which means it's going to cross the y-axis in negative land, or if we shift it up enough, it's going to cross in positive land. How do I know if it crosses the y-axis in negative or positive land? Find the y-intercept. Yeah, there's a chance it could go through the origin as well. Let's go ahead and find the y-intercept. You're going to want to get in the habit of doing that. It's probably the easiest point in general in any function to find. Plug in a 0, and I'm going to plug it into the original version. We have a pi plus e. I'm just going to throw that in the front. So remember, that's 6-ish. In your mind, you're just thinking that's 6-ish, plus the natural log of 5. The natural log of 5, we know, is what type of number, positive or negative? It's positive, right. Remember that the natural log function crosses at 1, 0. So if you take the natural log, or the log, really, of any number bigger than 1, it's a positive number. If you take the log of any number between 0 and 1, it's negative. So 6-ish is also a positive number, isn't it? So a positive number plus a positive number is a positive number. So now, indubitably, we know the graph crosses in positive land, and my graph is not very good, so I will grab it and slide it up. Somewhere in there. The domain is worth noting now. The domain of u, not your domain, but the domain of u, is the set of all x such that what? X is less than 6. Strictly less than 6. Good. The range, 24, 7, 365, is all real numbers. Which means the limit as x goes to negative infinity of u of x is what? This one's kind of tricky because the natural log of x flattens out so quickly, it almost looks like there's going to be a horizontal asymptote, doesn't it? But it's not. It does continue to go up forever and ever and ever, just very, very slowly. And so the y values do increase without bound to infinity. Log functions only have a vertical asymptote, no horizontal asymptote. The right-hand behavior, the limit as x goes to positive infinity, would be d and e. I probably wouldn't even ask you that because the graph doesn't even have right-hand behavior. It's a monotonic decreasing function, no local extrema, no global extrema. So those are kind of the interesting questions on this one. All right, we got 3 more to go. Let's kind of get through these pretty quickly. We'll do them together. D is m of x. And it looks like the parent function is the what? Absolute value of x, good. That's the one that looks like the v. It has the slope of -1 to the left of 0, slope of +1 to the right of 0, and a new version of Java is available. I've been waiting for this to come out. I asked for this for Christmas 3 years ago. I didn't know it was going to come to me on Mole Day. What a strange coincidence. It's not 6.02, it's 6 plus 2. Yeah, that was a stretch. Okay. Step 1, standard transformation form. The 6 in the front should go at the back. So we got the absolute value of something plus 6. Now we can combine like terms, can't we? On the inside, 2 plus 7, also known as 9. And it's a 2 minus 7. So somebody stop me before I lose control again. 2 minus 7. What is it today? It's -5 today. That's what it is every day, not a 9. What is it with me today? You don't have to answer that. I don't know. 2 minus 7 is -5. Now, x halves, that's negative x halves actually. That we're going to write as -1/2 times x. -1/2 times x. All right, so what does it mean to be inside the absolute value function? Well, it means that you are inside the absolute value. Duh. So inside now, we have to factor out the -1/2. And that leaves us an x plus, so what do you get when you factor a 1/2 out of a 5? No, that's 5 times a half. We want 5 divided by a half. 5 divided by a half is the same as 5 times the reciprocal of a half, which is 2, also known as 10. Okay, so again, if you want to do that off to the side, 5 divided by 1/2 is 5 times 2. That's 10. If you mentally redistribute, -1/2 times 10 is -5. You got it correct. Now we could do one other thing here. You can either leave the negative inside, or you could say that that's the absolute value of a negative number, which is always a positive number. You can even bring the 1/2 out front. So another version of this could be the absolute value of -1/2 is +1/2. You could bring it out front, and then you wouldn't need parentheses. Either one of those is technically correct. The difference is the A value versus the B value. Because the slope is 1 in this case, we're saying a vertical compression by a factor of 2, which is the bottom line, is equivalent to a horizontal stretch by a factor of 2. It works the exact same way. It's a 1-to-1 exchange now on the vertical and horizontal compressions. And apparently, having a y-axis reflection is as if we had no reflection at all. Why is that? What type of symmetry does the absolute value of x have? Y-axis symmetry. If you do a reflection across the y-axis on a function that has y-axis symmetry, you get the same graph. So kind of interesting the way that one works. All right, so let's just talk about the transformations from left to right. The bottom version is going to be, again, a vertical compression by a factor of 2, left 10, up 6. The one right above it is a y-axis reflection, which we won't see, and a horizontal stretch by a factor of 2. Then left 10, up 6. All right, so for this one, since the original function does have a point at the origin, we're going to follow it around. It's going to be now left 10 and up 6. So that's the new vertex. Any point that essentially is originally the origin is going to be now at whatever the transformations are, at the point C, comma, D. So -10, 6. I'm going to put those there. There's the new vertex. This graph opens up. And I'm going to draw it a little bit flatter than a slope of 1. Maybe I'll come in here in kind of that mustard yellow again, and I'll draw the original function. It's kind of interesting to show here, if you vertically stretch this by a factor of 2, vertically compress it by a factor of 2. That's like the bottom line, having the 1/2 out front. That's the exact same as having the 1/2 on the inside, which would be a horizontal stretch by a factor of 2. Now, not every function is going to be the same dilation on either axis, horizontally or vertically. But y equals x and y equals the absolute value of x are the exact same because the slope is originally 1. All right? So you can accomplish the dark blue graph from the original V either by compressing it vertically by a factor of 2 or stretching the x values horizontally by a factor of 2. Kind of nice to show that on there. But anyway, the dark blue graph is our final graph, and that's all we have to show. So the domain is what? All real numbers. Yeah, the range is the set of all y such that y is greater than or equal to. We actually hit the bottom low point of 6. Do we have a global min? Yes. Do we have a local min? Yeah, it's the same thing. We have a local and a global min of y equals 6 at x equals negative 10. Do we have a global max or a local max? No. No, we don't. Is this function monotonic? Is it monotonic decreasing or monotonic increasing over its domain? No. It's much more exciting than monotonic. It goes down and then it goes up. Ooh. Ooh, okay. Notice it doesn't have symmetry anymore. The plus 6 didn't mess up the symmetry, the moving it up and down, but moving it left 10 units messed up the y-axis symmetry, which is why it's important that you reflect it across the y-axis first, because before you shift it, because then if you reflect it across the y-axis first, you'll get the exact same graph. So you still have to do your transformations in the order your Aunt Sally requires them if you're doing it as a sequence. But because we know how the graph is going to end up looking, we don't necessarily sketch them that way. All right, P of t, that's the next one. What's the parent function on P of t? Square root of x, right, or square root of t, whatever you want to call it. The variable here is t. That shouldn't really matter. That's the one that looks like this. It's like half of your parabola opening up from the origin. Now, because it does start at the origin, the point 0, 0 is unaffected by any dilations or reflections. That's the point we're going to follow around with the c and d value. Step 1, put it in the standard transformation form. This one is pretty darn close. The outside is good. The a value is 1. The d value is plus 1. It's already back there. So on the inside, we just have to, first of all, we'll put the negative 3/2 term first. It's better to do it in terms of 2 steps instead of 1 and mess it up. So I'll put the t term first, and notice it's still negative. And now under the radical, that means inside the function, I'm going to factor out the negative 3/2. So when you factor it out from itself, you're left with a 1, so you just get a t. You are going to change the sign on the second term. What do you get now when you factor out a 3/2 from a 2? What's 2 divided by 3/2? Is it 3? Is it a third? Nope, the 2's don't even divide out this time. They double to give you 4/3, right? It's always what you started with, 2, divided by what you're factoring out. You can do it off to the side, change, stay, change, flip, you get 4/3. And if you mentally redistribute, you'll see your 3's do divide out now when you distribute. 4 divided by 2 gives you 2. So it's a real quick check right there when you mentally redistribute to make sure you did it right. So there it is in standard transformation form. Let's go ahead and list the transformations here. Don't tell me, don't tell me. The negative under the radical in front of the t is a y-axis reflection. Is that right? Yes. Okay, I'm redeeming myself this Monday. The 3/2. Is 3/2 bigger than 1 or greater than or less than 1? Sorry. 3/2. It's 1.5, right? So it's bigger than 1. So just because it's a fraction doesn't mean it's less than 1. So 1.5 being bigger than 1, is it a stretch or compression horizontally? You might think stretch, right? Because 1.5 is bigger than 1, but it's in the inside, so it's the opposite. It's a horizontal compression by a factor of 3/2. 3/2 is bigger than 1, so you don't need to flip it. We're making it 1.5 times wider. Then the minus 4/3 is right 4/3 and the plus 1 is up 1. Now we're ready for the sketch. There's no asymptotes on this one, but there was the original point at the origin. And because we went right 4/3 and up 1, that's the new location of the origin. 4/3, 1, we'll put a dot right there. And now there's 4 ways to draw that graph from there. You could draw it up and to the left, down and to the right, up and to the right, or down and to the left. We just need to figure out which one of those it was. All right? So if we reflected the original function across the y-axis, that's going to make it look like, oops, not like that, like this. And is that right? Ah, that's an x-axis reflection. Very good. So the y-axis reflection makes it look like that. We don't show the dilation. We don't show that we compress it horizontally by a factor of 1.5, but what that essentially does is it makes the graph steeper. Okay, it's kind of the conservation of mass. When you compress it horizontally, it buckles up a little bit, right? So it makes it a little bit steeper. But that's the final shape. So from this new vertex, or starting point, I should say, it goes up and to the left. Now, in this case, you could find the y-intercept, but there is no doubt that it crosses the y-axis in positive land. So you don't really have to find it in order to get the graph correct. I might still have you find it. Let's go ahead and find the domain, one that we can verify algebraically if we needed to. It's the set of all t in this case instead of x. I don't think I would necessarily count off if you went back to the old faithful x. But try to use the variables that are given. The set of all t such that t is less than or equal to 4/3. Yeah, and if you don't trust your math, remember you can come up here and say 2 minus 3/2 has to be strictly greater than or equal to 0, and you could verify it. The range now, we still use y for the range because the name of the function is p, but we still refer to them as y values. It's going to be from the graph, everything bigger than or equal to 1. What is the limit as x goes to negative infinity on p of t? I guess it should be as t goes to infinity. What is that? As we go out to the left on the graph? Yeah, it's infinity. Very good. Yeah, y'all did say that over here. It's infinity. It increases without bound. That's an ugly looking infinity. There we go. And the right-hand behavior doesn't exist. This graph stops at 4/3, so it would be D and E if I asked it to you, but I don't think I'd even ask it. This one is or is not monotonic? It is monotonic, right? It's decreasing. It's also 1-to-1. I don't think we've talked about that yet. Do y'all know what a 1-to-1 function is? To be a function, every x can have no more than one y value, but like x squared, the y values can come from more than one x value. A 1-to-1 function means that every x has only one y, and every y has only one x. So that would be a function that not only passes the vertical line test, but also the horizontal line test. And this one does pass the horizontal line test. So it's also 1-to-1. Let's go ahead and throw that on there. It's 1-to-1. You can write it like that. Or you could say 1:1, and we'll just say that it passes the horizontal line test. Continuous functions that are monotonic are also 1-to-1. That's going to be kind of important later on once we start talking about inverses. All right. Anything else to say about this guy before we move on to the last one of this example? I started off with a nice fall burnt orange, and then I switched to like pumpkin orange, which I guess is still kind of fall. Yeah. Very good. All right, x of t. This one's kind of weird. We're calling the y values on this graph what? X. Why? Just to confuse us again on a Monday morning. So the function's name is x. So when we graph the x of t values, they're going to be on the y-axis. And on the x-axis, we have t values. Sweet. All right, what's the parent function here? Is it 1 over t? Yeah, we only have one parent function that is a ratio, right? That has a fraction in it, and it's the 1 over t function. So since this one was a fraction, it's going to be the 1 over t function. But this one is going to be hard to put into standard transformation form because we don't just have a t in the denominator, we have a t also in the numerator. And that's going to be a problem if we leave it in this format. So guess what we get to do? We get to do something else before we put it into standard transformation form. Anyone know what that something is? The problem is telling you what to do if you listen carefully enough. If you put your ear right up against here, it says, divide me. Yeah. It says, divide me. Please divide me. That's what we're going to do. It's 4t minus 3 divided by 2 minus 5t. So that's exactly what we're going to do. We're going to satisfy its wishes. We're going to divide it. So the numerator, we'll do this off to the side, the numerator goes inside the house, and the denominator, which I'm going to write as negative 5t plus 2 in descending order, goes outside the house. The numerator we call the dividend, and the denominator we call the divisor. The numerator is the dividend, the denominator is the divisor. And because they're both t to the first, we're going to be able to do this division. All right, so step 1, how many times does negative 5t go into 4t? Long division of polynomials, you did in Algebra 2. Well, that's the same thing as saying, what is 4t divided by negative 5t? So do that off to the side. What would happen to your t's? They would divide out, and you're left with what? Yeah, negative 4 over 5, right? So that is the first term in our quotient. Now the way that you handle the rest of the terms is you distribute from up top. You remember doing that. You just look at the first terms to get the first number. What is negative 4/5 times negative 5? T? Well, it should be 4t. So you write it underneath the first term, and it is. And now negative 4/5 times positive 2 is negative 8/5. So you write the constant underneath the next constant. So you distribute from on high. Now the next step is to subtract. And because you have multiple terms, you're going to have to distribute a negative, which means you change both signs. So I use purple there to show that. You subtract, so you change both signs. 4t minus 4t, you should get 0 there. If you don't get a 0 here because these aren't the same, you did the division wrong in the first step. And now we get to add two constants. Negative 3 plus 8/5. Negative 3 is how many fifths? If you multiply by 5 over 5. 15. So what's negative 15 plus 8? Negative 7/5. And again, if you need to do that off to the side, that's where you do it. Fractions are numbers too, and we love them in this class. Now you try the division again. Does negative 5t go into negative 7/5? That is, does a t to the first power go into essentially a t to the 0 power? No. Things can go into other things that are the same size or into something that's larger, but they can't go into something that's smaller without getting fractions again. So we're done with the division process. Now, look at this. 38 divided by 6. That was an improper fraction back in the day. You remember that? When you first learned mixed numbers, you did the same thing. You did 38 divided by 6. 6 goes into 36 without going over 6 times. And then you multiplied and you got 36 and you subtracted. Did 6 go into 2? No. So 2 is called the remainder. So that means you can write 38/6 as the quotient 6 plus the remainder 2 divided by the original divisor. And then you wrote that as a mixed number, 6 and 2/6. Or maybe even simplified that one to 6 1/3. So that's how you can rewrite a fraction. It's the quotient plus the remainder over the original denominator or the original divisor. So that's what we're going to do here. We're going to rewrite x of t now. X of t is our quotient, negative 4/5, plus the remainder, negative 7/5, over the original divisor, negative 5t plus 2. Oh boy, that's a pretty looking number. We'll just write it like that. The quotient, negative 4/5, plus the awesome fractional remainder of negative 7/5 over the original divisor. All right, now we're able to put that into standard transformation form. Because now we got the t out of the numerator, there's only one t visible. So now we can actually start the problem. So that was just like a warm-up to the problem. Yeah. The problem before the problem. All right, so now let's go ahead and put it in standard transformation form. The negative 4/5 that's at the front should actually go at the back. The negative 7/5 in the numerator, I'm going to kick it off to the side and call it negative 7/5. And now we're left with a 1 in the numerator. You can kick any number out of the numerator and just put it off to the side. And now in the denominator, inside, I have to factor out the negative 5. And that leaves me with a t minus 2/5. Wow, this is a fun problem. T minus 2/5. Still can't write that 5 nicely. There it is. So don't be afraid of fractions. We have it now in standard transformation form. So to talk about the transformations, the one in front, that's an x-axis reflection. The 7/5, 7/5 is greater than 1, so that's a vertical what? Stretch or compression? If it's in front, it's exactly as what you would think. It's bigger than 1, so it's a stretch by a factor of 7/5, right? 1.4 times taller. The negative 5 inside, that is going to be a, let's do the y-axis reflection first. And then the 5 is going to be a horizontal compression, yeah, by a factor of 5. Then we're going to pick it up and move it right 2/5, and then down 4/5.
Just a quick reminder, picture retakes for 10th and 11th graders are tomorrow.
All right, we can finish the graph here in the minute and a half that remains.
Picture retaken, or you were absent the first round, you will be going during your English class tomorrow. Thank you.
Right 2/5, that moved the vertical asymptote, which was at 0, so you draw it there. Down 4/5, that moved the horizontal asymptote. So now we redraw it down there at negative 4/5. Now what's interesting is you're taking the original function and you're reflecting it across both the x and the y axis. Those are going to undo each other, and it's going to be right back where it started in quadrants 1 and 4. All right, we're going to look at this one again tomorrow, and I'm going to show you how you could have simplified before we sketched this one, and it made it a lot easier. All right, so get going with that worksheet if you haven't already, and we'll see you back tomorrow.